Hello, everyone. My name is Nicole Sultanam, and I am the session chair for Look, Learn Language Models. We have a fantastic lineup of papers today, including 6 honorable mentions. And we're going to get started with Dazhen. Dazhen, please cue your slides. And Dazhen is going to talk to us about AdversaFlow, visual red teaming for large language models with multi-level adversarial flow. And a reminder for the audience to please don't wait for questions, post them on Slido promptly because of the delay so that we can address them promptly when the presentation ends. And Dazhen here has received an honorable mention for this work, so congratulations. So yeah, let's get started.
Okay, thank you for the introduction. And I'm so happy to receive the recognition from the community. Okay, today I will introduce a work titled AdversaFlow, visual red teaming for large language models with multi-level adversarial flow. Large language models such as ChatGPT and Cloud have shown great power. However, ethical issues and security concerns have emerged, such as using large language models to create fake news or support illegal activities. Various techniques such as supervised fine-tuning, reinforcement learning from human feedback have been used to align large language models with human values, as well as red teaming. Red teaming is a method used to identify and fix model vulnerabilities by constructing adversarial cases. To address the low scalability of manual red teaming, many automated methods have been developed. For instance, the work by Pearson et al. And Casper et al. Both use large language models to generate adversarial prompts. However, automated red teaming methods still face many challenges. Adversarial training aims to improve both models simultaneously. The target model should improve its overall performance based on the evaluation of its responses. Similarly, the red team should adjust according to the target model's feedback to enhance its attack capabilities. However, some undesirable situations might arise during this process. For example, when the red team discovers an attack that works, it may repeatedly generate similar prompts to easily obtain high reverse. This may lead to the red model losing the comprehensiveness of the attack. In addition, the target model may perform well in adversarial prompts after red teaming, but lost the ability to handle general conversations. Currently, visual analysis have been used to model diagnosis, including diagnosing model security issues. Graph and AEVs visualize the activation pathways of images in models to explain the process of adversarial attacks. Inspired by these works, we consider that visual analytics can be an excellent approach to improve the model red teaming. Integrating visualization with red teaming is also challenging. First, the red teaming process may generate massive outputs, so it is important to consider how to provide both an intuitive overview of the chains and the specific failure prompts. Second, since large language models are sequential models, fluctuations in the initial words can impact the robustness of the overall response. Therefore, supporting fluctuation analysis is also essential. To address the first challenge, we propose a visualization design called multi-level adversarial flow. For the second challenge, we devise a distribution-based metric for assessing the likelihood of the token transitions. In this study, the taxonomies used are based on the work by Wang et al., which classifies prompt risk categories into 5 types and categorized the model responses from benign to toxic into 6 types. Next, I will introduce the overall design of our system, AdversaFlow. We first designed a model manager that supports automatic red teaming. Then we designed a comprehensive set of metrics for various aspects of the model, including security, diversity, capability, and differentiation. Finally, we designed a visual interface based on the requirements to analyze patterns in the red teaming process and provide interaction to give feedback to the model manager. Firstly, let me explain the red team framework used in the model manager module. In our red teaming framework, the primary components involve the red model, target model, and reward model, which are interconnected. The red model is fine-tuned from Llama 2. In the framework, we first extract some seeds from the database to generate a seed pool. The red model samples seeds from the seed pool at a certain ratio to generate a new adversarial prompts through a few short learning process. The target model can be any open source large language model. In the framework, the target model receives adversarial prompts and generates corresponding responses. In the framework, the reward model scores the responses of the target model, allowing these responses to be categorized into benign and toxic classes based on the scores. The benign responses will be fed back to the target model for revises and updates. The toxic ones will be fed back to the red model to improve the capabilities of the generation. Meanwhile, the corresponding toxic prompts will be inserted into the database. Next is the metric evaluator. Here, the safety and effectiveness of the large language model should be taken into account. For the security metrics, we designed attack success rate and average toxic score. For the effectiveness, we consider accuracy and diversity. In addition, we propose that fluctuation analysis is also important to large language model security. Ideally, during the training process, the large language model's performance may have initially been poor, but it ultimately stabilizes to produce benign responses. However, sometimes the model responses can be highly volatile during the training process. In such cases, we are uncertain about the quality of the large language model's answer in the future. Based on the idea, we define the prompt level fluctuation to be the distance between action types. Moreover, since large language models are sequential models, the initial few words of the responses may influence the subsequent outputs. If the initial tokens tend to follow the adversarial instruction, the final answer is likely to be toxic. Therefore, understanding how easily the starting tokens will turn into the risky tokens can reflect the fluctuation of the response toxicity. To calculate the token level fluctuation, we count the top n risky token sequences as a preparation step. We first calculate the distance between the model's response and each risky response. For the token sequence of both the model response and the risky response, we measure the probabilities of their tokens. Then, based on these probabilities, we compute the Euclidean distance of the first k tokens, which serves as a distance from the model response to a particular risky response. Then we take the minimum distance as the final value. Next, I will introduce the visual interface. Control panel includes buttons related to model management and training management. The embedding view shows the distribution of the dataset in the embedding space. The metric monitor contains a radar chart, displays the overall performance of the model, and a dual-axis line chart to simultaneously show the changes in multiple metrics. The adversarial flow illustrates the performance changes of the target model during the iterative training process. The instance list provides detailed information of the prompts and responses. And the fluctuation view supports the analysis of prompt level and token level fluctuations. The adversarial flow is the key component of our system, which is divided into 3 levels, progressing layer by layer. The adversarial flow contains a training flow and a validation flow. In the first level, the training flow displays an area chart showing the change of response toxicity The color encodes the toxicity levels, while the width of the flow represents the amount of each subset. Scrolling the mouse, the AdversaFlow changes to level 2. Here, the training flow spreads and presents the detailed information of each iteration. The colors on the left side of each subplot encodes different risk types. The flow in each subplot encodes the prompts of certain risk type, receiving responses of a specific toxicity level. Level 3 presents a more granular analysis view. By clicking on the nodes or flows in the Sankey diagram, users can observe the trends of specific risk types and the toxicity levels. Additionally, when conducting fluctuation analysis, the validation flow can display the fluctuation path of the selected prompt. Then we move on to the interaction design of the visualization. First is the model uploading and parameter setting. You can just upload the model from the file explorer and set the parameters for the training. And then is the metric analysis. You can select different metrics for the monitor. Then is the interaction of the adversarial flow. Then is the interactions of the fluctuation analysis. Then is the setting of the sampling rate. You can just adjust the sampling rate of the different seeds. And we can add some seeds to our database. For the evaluation, we designed 2 case studies. The first one focused on balancing the model performance across risk types and multiple metrics. The second one focused on the fluctuation analysis, aiming to pinpoint uncertain prompts to examine the model's vulnerabilities thoroughly. Experts provide feedback from effectiveness, expressiveness, and usability. We summarize that the system improves model security through 2 main uses: exploring for insights and adjustment for the fine-tuning. In case 2, the expert discovered a vulnerable model response through fluctuation analysis. Modifying the response test can change the target model to refuse to respond. In addition, we also conducted a quantitative evaluation. The result demonstrated the effectiveness of our system. The overall attack success rate decreased from 87.2 to 44.3, and the toxicity score dropped from the 0.209 to 0.146. However, our work still has certain limitations. Future work involves enhancing the scalability of the AdversaFlow, enriching the metric and datasets in evaluation, supporting the analysis of the advanced jailbreak attacks, and investigating LLM's behaviors in micro level. Here concludes our paper. Thank you for listening.
Thank you, Dazhen. A wonderful presentation. We don't have any questions on Slido at the moment, but do follow up on Discord for any questions. We are a little bit over time, so unfortunately, we're going to have to switch over to Minsuk for the next presentation, where Mr. Kahng is with us today, and he's going to talk about LLM Comparator, interactive analysis of side-by-side evaluation of large language models.
All right. Can you see my screen?
Yes.
Yes, great. Hi, everyone. I'm Minsuk Kahng, a senior research scientist at Google in the People Plus AI research team. Today, I'll be presenting our work called LLM Comparator. So how do people evaluate their large language models? So let's say you've trained a new LLM to compete with a state-of-the-art model like GPT or Gemini. The first step is to collect a set of test prompts and gather the model's outputs for these prompts. And traditional ML evaluation often involves comparing model outputs to ground truth answers. However, for generative models, it's infeasible to define ground truth because there's no single short answer for each prompt. So recently, a new popular approach called LLM method judge has emerged. And in this method, we compare our model's response to a baseline model's output rather than a ground truth. And we ask another LLM to act as a judge. For example, we can craft a prompt like this. So act as a judge, given a user's question and two different answers, choose which one is better and explain why. Then this method produces reasonably good results. And last year, we noticed that several teams at Google were using this approach, but they faced several challenges. For example, let's say if a new model outperforms a baseline model 55% of the time, which is slightly higher than a random guess of 50%, then they ask this question, should we adopt this new model? In many cases, the answer is no, because we cannot make a decision solely based on this single number. So there's a concern that the remaining 45% may contain critically flawed answers. And we wanted to better understand how these like LLM developers use this evaluation methods. We talked with the researchers and engineers at Google and identified several key user needs. First, we found that people wanted to know which types of prompts the model struggles. For instance, if a model underperforms on coding-related tasks, it might not be ready for release. Second, they also wanted to read individual outputs, a process they called eyeballing, to get a sense of what each output's about. Third, advanced users want to extract features for flexibly slicing data and computing metrics. And to address these needs, we designed and developed a new visual analytics tool called LLM Comparator, which is designed for researchers and engineers to evaluate their large language models, focusing on the following three key analytical questions. First, when? In what conditions does a model perform better or worse than a baseline? Second, why does this LLM judge method determine one model performs better? Third, how do two models' outputs qualitatively differ? And yeah, I'd like to show you a demo of our tool. In this demo, let's assume we've developed a model called Koala, and we are comparing it to a baseline model called Alpaca. And we have a test set of around like 400 user prompts, and we ask another LLM, judge LLM, say Gemini, acting as a judge to evaluate which model's response is better. So let me show you the demo. So when we load an LLM method judge evaluation results into the tool, here's what we see. On the left side, there's a table. Each row represents an example from the test set. And we have several columns. The input prompts and the blue column shows a model's response from the Koala model. The orange column shows the response from the Alpaca model. And there's a score. Here, a positive score means the judge determines model A was rated better. And yeah, it was, we take the score based on the average from 6 LLM judge runs. And next to that, we have a summary explaining why the LLM judge want to be better. Okay, and now let's looking at the right side, there are several charts. So we have the histogram shows the distribution of scores. Below that, we can see what conditions a performs better. And these are predefined categories of prompts, and we can filter the examples based on that. Below that, next, we can see why the one model is rated better through something called rationale summary. So it clusters the reasons why the LLM judge preferred one over the other into several themes here using an LLM-based clustering method. And for example, if we look at the first one, it says it provides more comprehensive, detailed information. And we can see in like 143 cases, A was judged better for that reason, while B was only 18 for its cases for model B. And then users can dive into these into certain cluster by looking at the individual examples. For example, this one, for the prompt, who was the president of Brazil, we can see that model A's response is much more detailed, while B is very simple. Next one as well. So now, this is where the tool becomes extremely powerful. As users continues to explore it, they can actively start forming hypotheses about the behavior difference between two models. For instance, they might notice a pattern like, oh, looks like A uses numbered lists a lot and well organized with that. Then what they can do is they can test this hypothesis by creating a custom function here. So using a regular expression that looks for a new line followed by a number, then a space. Then we can click the run button. What's happening here is the tool calculates this instantly. And yes, okay, the model tends to generate number lists more often than the second model, which confirms my hypothesis. And this might be one factor why model A is judged better overall. So yeah, this way, like users can discover some insights about models' behavior, which could help guide their decision-making process on whether to adopt this particular model. So yeah, I just want to highlight the key concepts of the tool, the demo I just showed you. So it provides three complementary ways to extract data slices from our data. So first, there are subgroups of prompts that are predefined and stored in the data set based on which is already known to be important. Second, the tool automatically extracts groups using LLMs. We developed an LLM-based clustering method combined with embedding similarity. Lastly, users can also define groups on the fly using functions, and users combine these three methods flexibly to analyze their data according to their needs. We conducted an observation study for qualitative evaluation. So we invited those who have internally used the LLM judge method, let them analyze their models and observe their usage. And we discovered a few interesting patterns. I'd like to share two of them. First, as seen from the demo, users can formulate and test hypotheses by examining individual rows and defining patterns. Second, users were able to verify some known undesirable behaviors. For example, they know LLM sometimes generates same sentences repetitively, and they were to identify these patterns by using our JavaScript-based custom functions. Another example is, many users want to check if models explicitly state when they don't know an answer, rather than hallucinating or producing unsafe outputs. So they checked for phrases like, okay, I'm sorry, but I can't, like using pattern search. This helps users ensure their model is performing as anticipated or if there's an issue. And yeah, I'm very excited that the LLM comparator tool has been used by many teams at Google, leading to improved model performance and dataset quality. And this year, more than 1,400 users have used it for over 20,000 evaluation runs. And we have also open sourced the tool, making it publicly available following our pair team's long tradition. And the tool was also introduced at Google's I/O event, the biggest company-wide event, and we released it as part of the Google's Responsible Generative AI Toolkit. And yeah, there are several interesting future research directions. First, now that we have extracted structured attributes from unstructured data, there are many opportunities to further leverage the revisit traditional multidimensional info-based method. Second, while we automatically extracted clusters, which captures high-level patterns, they might not always align with people's mental models. And custom functions have some flexibility, but have limited expressiveness. And I believe there are opportunities to combine the strengths of these two approaches. Yeah, that's all for my presentation. Thank you very much.
Great talk, Minsuk. We have a number of questions for you. We can probably address a couple of them. So the first one is, using an LLM as a judge is interesting. Is there any concern/limitation with evaluating an LLM with an LLM?
Yes, of course. There's of course, it does not guarantee that this LLM-based evaluation methods provides the correct results. So usually, this LLM-based evaluation method is used before we conduct a human evaluation. So we can expect that the human evaluation may provide better results, but it is much more expensive. So before we conduct human evaluation, developers can quickly conduct this LLM evaluation first to see whether it's okay. If it looks okay, then they can move on to the next stage of conducting human evaluation.
Awesome. We also have another question. The first question was from Devin Lynch. The second question is from Richard Brath. And it is, did you consider additional markup to facilitate faster human scanning of the content instead of structure? For example, format salient phrases, heavyweight font.
Yeah, certainly. Yeah, that's a great idea. So currently, you probably noticed that we highlighted terms that appear both in the first model and the second model. So it's an option which users can toggle. But certainly, if we can highlight some terms based on the saliency, we may be able to from the LLM-based evaluation method, if we can compute which tokens are more salient, we can highlight them. Yeah, of course, that'll be super helpful. Yeah, thanks for the suggestion.
Awesome. There are a few other questions, some of them fresh in Slido, so I would encourage you to continue this conversation on Discord. Thank you once again, Minsuk. And so we have Ling Gao for our next presentation. And Ling Gao is going to talk about fine-tuned large language model for visualization system, a study on self-regulated learning in education.
Yes. Thanks for Nicole's introduction. And hi, everyone. I'm Ling from Fudan University, and it is a great honor to present our paper in this section. And this section is about how we can combine the process of fine-tuned LLMs with visualization systems. And we also conduct a study on self-regulated learning education following the proposed framework. And let's start. Nowadays, LLMs have captured significant attention and opened new avenues for tackling specialized domain problems. And to extend its performance on domain problems, we often fine-tune the model with high-quality data, making the model more focused and allowing us to modify the model output to a certain extent. The previous visualization systems often used basic methods or models to solve domain problems. And many researchers are also considering integrating LLMs into the whole process. Currently, their power can be leveraged in several ways, like external knowledge bases, prompt engineering, agent settings, and data fine-tuning, and so on. And both LLMs and the visualization system can help solve complex domain problems. So what if they were combined for a complex task? Due to their distinct performances, I think they will encounter some difficulties, complicating the optimal use of their strengths. And we summarize and propose these 3 alignment tasks. And we define alignment here as a mutual adaptation and coordination between LLMs and the various elements like domain knowledge, visualization, and interactions. And the first one is the adaptation of LLMs to domain problems. Due to the strong domain barriers in these problems, general LLMs are found difficult to handle complex domain knowledge. And the second alignment task is synchronizing with visualization. LLMs often lack knowledge of visualization systems or visual analytics, and we should internalize the visualization process and the visual mappings as knowledge or action in the model. And the third one involves understanding and enhancing interactions with LLMs. LLMs need to understand the various types of interactions and how to provide personalized interactive recommendations is also very important. So based on these aligning requirements and the traditional framework of visual analytics process, we propose the conceptual framework to illustrate the relationships and the integration process. The red labels in the framework highlight the connection that are introduced or altered by the involvement of fine-tuned LLMs. Data fine-tuning helps model learn to know knowledge and apply the knowledge to solve problems, which meets the first alignment task. And the fine-tuned LLM needs to understand the origin intent of some visual designs, including design purpose, data features, and the communications of relevant insights. So refinement strategies can be extracted from these intents. LLMs should also align with human preferences, habits, and behavior patterns. This adaptation enables the LLM to deliver intelligent assistance during user interactions, whether through natural language processing or visual interface engagement. To be more practical, we derive insights from the conceptual framework, and the general workflow process undergoes three phases. The first one is task identification, and the second is design mapping, and the third one is user alignment. At each stage, we have summarized some common but achievable guidelines to meet the three alignment tasks. And due to the time limitation, you can refer to detail about the workflow in our paper. And to put this conceptual framework into practice and demonstrate the feasibility of this conceptual framework, we conducted a study on self-learning in education, because we found that the combination of intelligent education and the visual interaction is becoming increasingly important. And in this process, domain expertise of LLMs is essential to ensure the reasonable model output for the students or the teacher. And at the same time, we found that very few studies focused on the entire learning process, and the online learning platforms have become the main learning method for many people. Therefore, we treat the self-learning task in AI as a domain task, and we collect and process data related to AI courses, such as textbooks, notes, handouts, and so on. In the first stage, task identification, we conduct a preliminary study consisting of expert interviews and student surveys to identify the design requirements of the visualization system and the specific fine-tuning task for intelligent learning. The following stages will also construct tuning data around these three tuning tasks. So the entire LLM-assisted self-learning pipeline is shown in the slide. And here is a specific example of a data construction scenario. Normal Q&A interaction is crucial for us to engage with LLMs. Here, a student asks a question about the main components of an encoder in the transformer model, and we will train the model to respond following a logical chain of thought based on the structure of Bloom's taxonomy, which primarily includes the following four parts. This is a basic operation of instruction fine-tuning. However, on our work takes it further by asking follow-up questions based on the model responses. And we will recommend the information and ask triples beneath the Q&A, allowing users to add some triples to the network graph interactively to make the association with the visualization system to better understand the knowledge relationships and to have an in-depth understand for the students. And in other stage of self-learning, we have considered this type of extended interaction, enabling the model to perform 3 alignment tasks. And the specific operations can also be found in our paper. And after that, we developed a system named the TailorMine to implement the whole process. The whole process starts with the user uploading the learning materials, and the system will analyze the materials and construct the learning path for each student. And the student will learn in a problem-driven way, and we provide a range of intelligent recommendations, such as the questions different students like, and the connecting knowledge that is important for their understanding. And finally, enter the self-task phase to obtain their personalized self-evaluation and reflection. And our assessment needs to understand the impact of the fine-tuning process. So we started by evaluating the model performance, and we found that the accuracy of the answer was improved, and the hallucinations were reduced to a certain extent. And at the same time, the stability of answer qualities brought out by the fine-tuning technology is unexpected for us. And the model is also more in line with the user preferences. And in addition to the objective evaluation of the model, we also designed a user study with a control group for self-learning using TailorMine and GPT-4. During the study, we recorded the relevant observations and made the following findings. The first one, that we found participants generally performed well on tasks, and they can understand the knowledge points in depth. And the self-learning process for students were more planned and goal-oriented, encouraging their self-reflection. And the way they ask a question during the whole learning process became more easier, and their desire to explore issues intensified, fostering the exploration of new questions. We have discussed the future work in the perspective of TailorMine and the overall framework, hoping to make them more accessible and personalized. And thank you for your listening. You can learn more the paper by visiting the lab website or my homepage. And right now, I am a last year graduate student actively seeking for PhD opportunities, and I would be delighted to discuss any potential opportunities with you. Thank you.
Thank you, Lynn. Wonderful presentation. We have a couple questions on Spider. We have time for perhaps one. We have a question on, do you think your framework could directly use prompt engineering instead of fine-tuning? What's the difference?
It's a good question, and I think with the development of LLMs, and the LLMs will get more and more powerful, their domain knowledge will definitely improve. But for now, if we want to align LLMs with something like visual designs or our user preferences, I think there is no such personalized LLMs for us. And I also think prompt engineering is very challenging. And if we could design the perfect prompt for the most of the situations, I think it might be worth a try. And as to the difference between these two approaches, I think LLMs can fine-tuning LLMs can make our more controllable for the model. And the prompt engineering, on the other hand, is more flexible and accessible, gives us more space to have a try. Yes. Thank you.
Awesome.
And that's my
Thank
answer.
you, Lynn. Yeah, and thank you very much. There's another question on Slido, which is going to be transferred to Discord soon, and I would encourage you to continue that discussion there. And next up, we have Qingshun, and he's going to talk to us about advancing multimodal large language models in chart question answering with visualization referenced instruction tuning. Take it away.
Thank you for the kind introduction. Hello, everyone. My name is Zheng. It's my pleasure to be here to share our paper. And this work is a collaborative effort by myself, Chuhan, Ying, and Wei Zheng, and the authors are from HKUST Guangzhou and HKUST. Regarding the general background of our work, multimodal large language models, such as GPT-4 Vision, have emerged to enhance LLMs with the ability to perceive and understand visual signals. For example, by taking a screenshot of the VIS conference homepage and asking the GPT who might be interested in this conference, we can receive a precise and very comprehensive answer. Naturally, LLMs hold great potential for interpreting visualizations used through natural languages like short question answering and summarization. Our recent work even explored employing LLMs as an agent to conduct very complex tasks like scatter plot opacity optimization. However, before exploring future applications of LLMs in visualization, we argue that chart question answering is a foundation of empowering and evaluating LLM's chart understanding capability. You may ask, why does CQA matter? Firstly, training LLM requires instruction data to help the model construct the basic understanding of the given images. The data format is a triplet, including the target images, the task description, and the task output. We will find that the chart QA data naturally fits the formats as chart, question, and answer. So therefore, chart QA data endows LLM the basic chart understanding capabilities. Considering its importance, we naturally raise one research question: what makes the effective visual instructions for CQA? As you can raise numerous different questions towards a single given chart. Secondly, we observe that the leading open source and commercial LLMs choose a representative CQA dataset, chart QA, as the training data or benchmark for improving or evaluating their chart understanding capability. Also, here is another question: are existing chart QA dataset good enough for both training and evaluation? With the two research questions in mind, we first conduct an empirical study to investigate them, try to get some insights for further data optimization and model development. While chart QA is a very, very good work, it's inherently limited by the scope at that time, which is before the emergence of large language models. First, we identify notable biases in chart QA's chart distribution when comparing its image features with some real-world datasets. Here, we use BIGO for comparison. Also, they only include bar, pie, and line charts. The underlying reason is that chart QA's charts are collected from some limited websites, and they share very similar view styles. In terms of QA pair distribution, we analyze statistics from the two chart QA splits. The machine-generated set, which shown in the left pie chart, which is generated with traditional deep learning models, primarily focus on the basic data retrieval tasks, which do not require visual cues or compositional operations. In contrast, the human-noted set is more diverse, encompassing a wider range of question types. For comparison, here we also present a real-world chart space employing our work, which is summarized by a previous visual literary research. This space clearly diverges from existing datasets, highlighting the gaps in current works. Following, we break down the chart QA's human sets into fine-grained QA types, revealing some noteworthy insights. We also include the visual literary problems as a reference group. Notably, the high scores on chart machine sets can be sometimes misleading, as they will influence the overall performance metrics. In fact, LLM underperforming scenarios require numerical computations and visual comparisons, specifically when faced with some out-of-distribution chart types and question tasks included in the literacy tasks. In the second part, we employ 3 datasets to conduct instruction tuning ablation, including the chart QA human set, the machine set, and the chart QA table set. Our goal is to try to determine which dataset is most effective for training multimodal models' chart understanding capability. The results show that the effect of chart QA human set is a superset of the machine set, which significantly enhance the multiple performances across all question types, while the Chiokit machine set is less effective, primarily for improving basic data retrieval and the simple visual questions. Additionally, the chart-to-table set proves to be a very, very effective instructional tool when data tables are available. So in summary, the complex visual instructions are more effective. Drawing from the insight from the previous study, we propose a two-stage data engine. First, we want to conduct data filtering for efficiently utilizing existing data and ensuring appropriate training cost. Then we try to do data generation to optimize the existing data distribution. Our final goal is a data set with appropriate size while encompassing the whole real-world chart features and the QA tasks. However, directly utilizing all existing data sets can pose significant challenges. Here are some numbers. Lava as a leading generic MMM, which only require about 1,000K instruction data, while Unichart and chart systems use about 7,000K and even 40,000K data. This diversity highlights that it is very impractical to incorporate all available chart data into generic MS training. However, conventional filtering data approaches that sample the image data in the feature space can lead to very, very unbalanced chart distribution regarding the chart type, the layout, the trend, and the number annotation, and whether there is a data grouping. To address the issue, to achieve ideal balanced sampling, we first define the key properties that are important for chart understanding and build classify them, such as the chart type, layout, trend, number annotation, and data grouping. Then we conduct stratified sampling based on the fine-grained chart classes. Finally, we sample a subset of approximately 70K charts in the joint embedded space, ensuring a both diverse and comprehensive representation of the existing data sets. Notably, just as identified in our previous study, existing data sets exhibit very significant biases in terms of chart features. We try to mitigate the existing data biases through data generation. Generally, our framework encompasses 3 stages. First, we try to collect some examples, and then we expand the number of examples. Finally, we target covering the overall chart space through data augmentation. Specifically, the first stage is the retrieval augmented chart generation. We collect high-quality examples from previous studies and authoritative chart libraries, including VigaLite, Matplotlib, Seaborn, and eChart. Then our framework will try to retrieve some set examples according to a table similarity to serve as the in-context examples to improve the generation accuracy. The second stage is a visualization reference encoding augmentation. We will try to cover the overall visual encoding space and optimizing the chart distribution. So we will tell the LM all the reasonable modifications it can apply to a specific chart type. For example, we can tell the bar chart, it can modify the number annotation, the layout, and the color, and the grouping, and even the bar VIS. Through the two-stage generation, we can get a lot of very, very comprehensive generated data. Here are some examples. We can see that our pipeline produces charts that use very comprehensive visual encodings and is almost scalable to almost all common chart types and plotting libraries. Here is a more detailed example. It includes the chart-to-table translation and some question-answer pairs. We can find both basic tasks like data retrieval and some more complex tasks like find extremer and determine range. In the model part, we improve 2 design choices considering chart-specific feature. First, we unfreeze the visual encoders during the training phase. In contrast, most MMs developed that time choose freeze because they think that the original clip is already good at extracting the natural images features. However, our motivation is that the prediction clip underperforms in visualization scenarios. Second, considering charts are text-rich and they require fine-grained recognition, we integrate a mixture of resolution adaptation strategy for enhanced fine-grained recognition to improve the high-resolution feature. In the evaluation part, we first compare our model with the SOTA of open source models in the traditional benchmarks, including ChartQA and chart-to-table, which surpass the current leading models, but with much less data, showcasing the effectiveness of our data filtering and generation. Also, the evaluation studies demonstrate the effectiveness of our 2 model design choices. We also compare our model with the leading commercial models in the test split of our generated data. We find that our model outperforms commercial models in most tasks and even achieve comparable performances with GPT-4 vision. Finally, we present 4 interesting cases comparing our model with some SOTA MMs on child question answering. Existing MMs will often fail to understand visual mappings, such as the inverted axis, the truncated axis, the bubble sizing, and some area stacking. In contrast, our model trained with the visualization reference dataset showcase a better understanding of those visualization domain knowledges. Here are some key takeaways and conclusions. First, using the high quality and the proper size instruction data for understanding is very, very critical for generic MM training. So we try to cover the real-world child task space in the various visual encodings. Second, as a clip vision transformer doesn't perform well in the visualization scenario, unlike natural images, operating visual encoders significantly boost model performances. Lastly, charts are like document elements. They need a very, very detailed analysis. In this context, high-resolution visual features are very important. Thank you for listening. This is all about my presentation, and all the code and datasets about our paper are open sourced, and the discussion and future collaborations are very welcome. Thank you.
Thank you, Jing. We don't have any questions on Slido, but I do have one question. And in the meantime, Will, if you'd like to queue up your slides for presentation. Jing, I was wondering, have you looked or considered charts that have annotation overlays in them? Like, for example, arrows for trends, text annotations for context, etc. Have you thought about those? How would your pipeline support that?
Yeah, this is a very good question. Actually, I discussed some points about this question in my discussion parts, and my point is that this kind of QA, we call it referential QA, which means we use the arrow or rectangle to refer to some specific area in the chart. And actually, I think this type of QA will significantly help the model to learn some fine-grained analysis, especially for some related to some humans' intent, because we always try to use some symbol to express our intent over a chart, specifically in the visual analytic scenarios. But actually, this may be a part of our future work, and we will try to exploit. And then, in my opinion, I think this format QA will be very, very beneficial.
Queue up the next presenter. We have Chang presenting guided health-related information seeking from LLMs via knowledge graph integration. And this is also another honorable mention. So congratulations, Chen for this award.
Thank you. Okay, yeah. Hi, everyone. I'm Chen Wang. I'm currently an assistant professor in the University of Minnesota. Today, I'm presenting our study known as guided health information seeking from LLMs via knowledge graph integration. And so I'm here to present this paper today because the first author is already graduated working in Amazon, and now is his working time. But yeah, let's go to the paper. So nowadays, more and more people are shifting away from search engines like Google search and turning into LLM-based chatbot for information query. And this is largely due to chatbots' unique abilities to handle complex queries and provide direct and conversational responses. But despite all the unique advantages, LLM also suffer from hallucination, as illustrated in this famous example. GPT-4 once confidently claimed that 9.11 is greater than 9.9, which can be a bit risky when you want to have some accurate and reliable information. So why do hallucinations happen? Unlike search engines, where information can be directly inspected and verified, large language models encode knowledge within model parameters, which user cannot directly access or interpret. So this raises a question: what if language models could access external knowledge rather than relying solely on the knowledge encoded within the model parameters? Well, this leads to the smart research idea of retrieval augmented generation, which was also called RAG. So generally speaking, RAG uses an external knowledge base to enhance the LLM generation. It retrieves relevant information from external resources and feeds it into the LLM to enhance the generation, enable more accurate and reliable responses. Despite the improvements introduced by RAG, it doesn't solve all the problems, and the module can still generate inaccurate responses occasionally. So here is an example about in the medical context. Even with RAG, the GPT-4 still gives us unsupported statements. And more importantly, RAG doesn't address the challenges users often encounter when interacting with LLMs, such as information overload, limited support for verification, lack of exploration guidance, and the absence of clear indicators for achieving goals. And so please refer to our paper for more details on how we summarize the struggles from a literature review. But based on all those struggles, we tend to ask, is the generation stage the only point that external knowledge base can be useful? Could we also use the external knowledge base to directly enhance the human LLM interactions? And to answer this question, we present our study, known as Guided Health Information Syncing from LLMs via Knowledge Graph Integration. In this study, we use health information as a test base and consider knowledge graph as an external knowledge base due to the unique symbolic reasoning capabilities and the wide availability across many domains. So for example, here in this knowledge graph, the nodes would represent medical entities such as drugs, disease, and the edges will indicate relationships among those entities. And all those relationships are extracted from scientific literature, which ensure that they are solid and well-verified information. To achieve this idea of knowledge graph integration, the first challenge we encountered was the diversity of knowledge formats. So we can see here, human process information in varied and often unstructured ways. LLMs often output a very long paragraph, and the knowledge graph, they use a structured topological formats. Those different formats are all very different from each other, and how to merge them together to present a unified representation of knowledge to help users in understanding and interpreting. To address this challenge, we're thinking about using knowledge graph to scaffold a step-by-step information syncing process, where users actively and progressively constructing a knowledge graph centered around the topic of interest. So for example, here, the users query about which diet supplements may benefit Alzheimer's disease. Knownet will respond with a node-link diagram illustrating the connections between omega-3 and vitamin E to Alzheimer's disease, and also provide the corresponding text. And if the users then ask why vitamin E is helpful, the node-link diagram will update to include the new information about vitamin E's mechanisms of action by adding relevant nodes and edges to the graph. And this process continues as users ask additional questions. Based on this formulation, we can then further provide information validation using the literature contained in the knowledge graph. So for example, here we are able to verify all the relationships in the node-link diagram by directly linking them to the literatures in the knowledge graph. Additionally, we can merge the user's conversation history with a relevant subgraph to offer our personalized next step recommendation. And this approach builds on the widely accepted assumption that the concepts in the subgraph are more likely to be relevant for the next step exploration. Now let's take a look at how Knownet integrates the knowledge graph to create an enhanced human LLM interface.
To enhance user experience, Knownet offers two key features: information validation and next step recommendations. Information validation helps users verify the accuracy of the LLM responses. Next step recommendations are provided based on the current exploration and the structured knowledge in KG, guiding users to a comprehensive understanding of their topic of interest.
Okay, then let's talking about the technical details. We certainly do not have enough time to cover all the technical details, but here is a high-level overview of the system implementation. So when user first asks a question, we will collect response from the LMs and also retrieve relevant nodes from the knowledge graph, and then match them in a shared embedding space. This process produces text output along with a node link diagram that includes the validation information. The identified nodes in the knowledge graph are then used to expand a subgraph, which is aligned with exploration history to rank nodes in the subgraph, generating a recommendation pool for the next step recommendation. We demonstrate the effectiveness of no-net use cases and expert interview. And note that instead of just using like 2 or 3 use cases, we have in total 15 use cases to demonstrate the effectiveness of the system. We also observed some interesting patterns in the evaluation. We observed an increase in user trust, where users typically hesitate to rely on LM for certain critical information seeking, but they find those literature provided by no-net are very reliable and reasonable. We also see that users use the LM and knowledge graph to complement each other, and that they appreciate the on-the-fly summary and organization of the information provided by no-net. So to conclude, we propose enhancing the human LM interface by integrating external knowledge graph. The no-net system facilitates validation through literature for accuracy, next step recommendation for comprehensive exploration, and a step-by-step graph visualization for progressive understanding. We also acknowledge its limitations, including the scalability of the node link diagram and the varying types of user mental models when interpreting text, which calls for future studies to examine different types and formats of external knowledge. Okay, thanks for your attention, and I'm happy to have any questions or comments.
Thank you, Chuhan. We have 2 questions on Slido. The first one is from Zhang. Great talk. Wondering if there are errors or biases in the results of LLMs. Is it possible that the knowledge graph might exacerbate the trust in such errors, and how to avoid that?
And then try to and the question tried to ask whether the knowledge graph will actually increase users' blind trust in terms of knowledge graph. So I think the main reason we introduced the knowledge graph is that most of the information in the knowledge graph are directly extracted from scientific literatures. So in that case, the information provided by knowledge graph is basically the same as the information provided by scientific literature. So most of the things we will think it is reliable and validated information. But I would say that might happen sometimes that because like in the scientific literature, sometimes they also report studies like researched in the progress. So they may see some like benefits from omega-3, but it is validated in 1 or 2 studies, but not well recognized in the whole research community. So I would say in that context, it might give users a wrong impression that, okay, these results is more like still in debate, is not common agreements shared by the whole research community. Yeah.
Wonderful. There's another question on Slido, but we are a bit over time. So at this point, I would just encourage you to check those, and engage in discussion on Discord for those follow-up questions. And I just wanted to take an opportunity to thank the speakers once again for a wonderful session, and a special thanks also to the student volunteers running the Zoom and Discord. Thank you very much, and I hope you all enjoy the rest of the conference.
Yeah, thank you.
Thank you.
Thank you.
Thank you.